All right, I will now determine the conjugacy classes in an when n is greater or equal to 3. As mentioned in the last video, that our aim is to get the character table of the group A5 from that of S5, using the results that we have studied on restriction of representation to a subgroup of index 2. In the last video, we have written the character table of S5. Now it is the time to go for the character table of A5. So the first step towards writing the character table of A5 is to determine the conjugacy classes in A5. Fortunately, this can be done in the generality, that is, we don't have to restrict ourselves to n equal to 5. We can do it for any n greater or equal to 3. We can do it for any n greater or equal to 3. So yeah, let's consider two sigma and sigma prime, two permutations in Sn. So if they are, we have already discussed that if they are in the same conjugacy class in Sn, then they will have the same cycle type. Okay, but unfortunately, this does not hold when we are inside An. That is what I want to say is, suppose two sigma and sigma prime are in An. Suppose sigma and sigma prime both are in An and having same cycle type, then they may not be conjugate in An. So let me give you an example. In A3, you can just take sigma to be 1, 2, 3, this 3 cycle, and sigma prime to be 1, 3, 2. So these 2, 3 cycles, they are in S3 they are conjugate, but certainly in A3 they are not conjugate, because A3 is a cyclic group, hence abelian. So the conjugacy class of each of them is so the conjugacy class of sigma is singleton sigma, and so is for sigma prime. So what at most we can say in the generality is, for any sigma in An, the conjugacy class of sigma in An, that is conjugation by even permutation, is contained in the conjugacy class of sigma in Sn. And the above example shows that this containment need not be, this containment could be proper. Okay, that is what this above example shows. So since here we need not have an equality, and in fact we can have the containment proper. So therefore it is a very relevant question to ask when equality occurs and when not. If the containment is proper, then whether we can say something else, we can say something more or not. So these are very natural questions. We will now see them. So recall that yeah. So suppose sigma and sigma prime are in the same conjugacy class. Well, let me write like this, that suppose sigma prime is in the conjugacy class of sigma in Sn. Okay. So that means sigma prime can be written as some tau sigma tau inverse for some tau in Sn. If tau happens to be from An, then certainly sigma prime lies in sigma prime lies in An. So if tau is from An, then we can say that sigma prime lies in conjugacy class of sigma in An. Okay. if tau does not, if tau does not lie in an, then we are certain, then we are in a answer, then we are not in a situation which is quite clear whether sigma prime will lie in sigma prime will lie in the conjugacy class of sigma in an or not, because we don't know that whether there will be some other tau prime which is in an, such that tau prime sigma tau prime inverse will be sigma prime, that we don't know. But we will see that we can have that under a under a very natural condition. So suppose that, so before getting into the condition, let me try to motivate that. So what's the, as I said, that what do we want? We want to replace tau by a tau prime, whether tau prime will be in in an such that this happens, right? So from tau to tau prime, we have to from tau which is not in an, from that we have to get a tau prime which is in an. So what is the most natural way to get an even permutation, to get get an even permutation from an odd one? Simply we would like to multiply that by an odd permutation, or in particular even a transposition will work. So if I can find the odd permutation alpha not belonging to an, if we multiply a permutation, multiply tau by an alpha, then what we will get is an even permutation, right? Now we will see that whether we can make a suitable choice of alpha such that tau alpha sigma tau alpha inverse is sigma prime or not. Let's see whether we can make a suitable choice of alpha or not. As I said that this tau is not in an, we would like to replace that by a tau prime which lies in an. So how to get a tau prime from tau, where the tau is an odd permutation and tau prime is an even permutation? The natural way is multiply tau by some odd permutation. So we see that whether for any a suitable choice of alpha, we can achieve this or not. So if this happens, so now just see from the left hand side. So the left hand side is nothing but alpha sigma alpha inverse tau. Okay, tau inverse. And now what we know, so this is what we want to be sigma prime. Okay, this is what we want to be sigma prime. And now see that we will immediately achieve this if we know that this is sigma. Okay, we will immediately achieve that. So this shows that, suppose that if there is an odd permutation which commutes with sigma, suppose that we have an odd permutation which commutes with sigma, then certainly sigma prime will belong to class of sigma in an, right? This is what we have seen. This is what we have seen here, that suppose I have an alpha such that this conjugates with that, then this fellow, then if we choose tau prime by tau alpha, immediately we get this to be sigma prime as sigma alpha sigma sigma sigma. So we now have a condition that shows when the class of sigma in an will be same as the class of sigma in Sn. We have a sufficient condition. Namely, the condition is if there is an odd permutation that commutes with sigma. So in this situation, if this happens, then for any sigma that lies in the conjugacy class of then for any sigma prime that lies in the conjugacy class of sigma in Sn, that also lies in the conjugacy class of sigma in An. So this is what we have under the assumption of the existence of an alpha, an odd permutation alpha. Okay. So the natural question is, what happens if there is no such odd permutation? So in that case, certainly this is not so likely, right? Try to understand what we have proved, that if there is an odd permutation alpha, then this class, this there will be we will have an equality here. So if there is no such odd permutation, we might have an equality or may not have an equality. In principle, we will now show that in fact it will never have equality. And in that case, we will see that not only it will be, this will be properly contained in that, in fact the size will be the half of the size of this. This is we will show now. So that's very easy to see that if there is no odd permutation which commutes with sigma, then certainly what we said, then certainly what we get is the centralizer of sigma in An. The centralizer of sigma in An is same as the centralizer of sigma in Sn, because centralizer is the all permutations that commutes with sigma, and we have just assumed that there is no odd permutation which commutes with sigma. So therefore the centralizer will be same, and once you know that the centralizer will be same, then from that we immediately see that this is just, according to our orbit stabilizer theorem, two times or An this is this, and we can simply in the numerator we can simply replace this by this because they are now equal. So what is this? This is nothing but 2 times the size of the conjugacy class of sigma in An. So this implies that the conjugacy class of sigma in An, the conjugacy class of sigma in An is simply, the size is half of the conjugacy class of sigma in Sn. In fact, we will also show something interesting that so let me just say that what we are going to show is we have just seen that if there is no such odd permutation which commutes with sigma, then the size of the left hand side just becomes the half of the size of this. So the natural question is, what is there in the rest half? So this is what we will see now. You'll see that rest half is also, that also has a very nice description. So recall that the conjugacy class of sigma in Sn is basically the union of two things. First, the all conjugates of sigma with An. So basically this is conjugacy class of An in a sigma in An union all conjugates of sigma where alpha is an odd permutation, right? Because when alpha is even, that is precisely this An. Okay. Now let us recall that Sn has the following decomposition, coset decomposition, An and then An 1 by 2, 1 2. Okay. So all odd permutations lie here. Okay. So therefore any odd permutation indeed looks like, so the set of all odd permutations is precisely this set. So therefore in view of this, when alpha is odd, then alpha sigma alpha inverse is basically beta 1 to sigma 1 to beta inverse, okay, beta 1 to sigma beta inverse. So once alpha, so as beta runs over all even permutations, then we get, as beta runs over all even permutations, then we get exactly this set, right? As beta, because as beta runs over all permutations, then this will constitute all odd permutations. Let me just repeat: for any odd permutation alpha, we can write alpha as beta times 1 2, where beta is in n. Basically multiply alpha by 1 2, so you can call it beta. So then a typical element in the in this set looks like this, and from the other hand looks like this, and on the other hand anything, so any uh, uh, conjugation of 1 to sigma 1 2 by an even permutation of beta, by an even permutation beta, automatically lies in this set. So therefore we have now a alternative description of the set which is lying here. Let me just write that. So this is nothing but beta 1 to sigma 1 to beta inverse, where beta lies in an. Okay. So now what is this? Now it is quite clear. This is nothing but the class of this thing, conjugation of sigma by 1 to in an. Okay. And it is also quite clear that since the order, then the size of this is just half of this, then certainly this union has to be disjoint, and the size of this is so yeah. So again, let me repeat. So it is now quite clear that since the size of this is just half of this, so therefore this union must be disjoint. And this is the other half. Okay. So what we have got is, if there is no such odd permutation which commutes with sigma, then the conjugacy class of sigma in essence splits into two halves. So in one half is the conjugacy class of sigma itself, but inside an, and the other half is the conjugacy class of a conjugation of sigma by 1 2 in an. Okay. So this just splits into two halves. Okay. So now we have a complete description that what happens to the now we have a complete description about what happens here. So the situation is very clear. In fact, as I said, a complete picture we have. So if we have a odd permutation which commutes with sigma, then there will be equality. Then it will be equal. If not, then it will be divided. It will split into two halves. In one half, you will find this, and on the other hand, you will find the equivalence class of a conjugation of sigma, of some kind of a conjugation of sigma by 1 2 in an. Okay. So thus we thus we know that for a conjugate, for how to get what happens to the conjugacy classes of elements in an. Okay. Yeah. So with the help of this, now we will determine the conjugacy classes of elements in A5, because we will use that in we will use them in the determination of, in the determination of the character table of A5. So recall that in S5 these are the different representatives from 1 2 cycle, 3 cycle, 4 cycle, and then 5 cycle, 5 cycle, then 2 2, then 2 2, and then 1 2 3 4 5. So these are the different these are the representatives from all conjugacy classes in in S5. Since A5 is a normal subgroup, certainly it will be the union of conjugacy classes from the normality. So we will now we have to see that it's enough to see that uh, which one which one from this list is allowed to be, I mean which one is on this list is allowed to be in AN, and what happens to their conjugacy classes in AN, of course. So let's first see that this cannot occur in AN. Okay, similarly this also cannot occur. Okay, this will occur because of event permutation, and then again this cannot occur. So out of the 7 distinct conjugacy classes in S5, only four lie inside A5. So as I said, out of 7 conjugacy classes, only 4 conjugacy classes in SN lie actually in AN, but we just have to make sure that the conjugacy class of the conjugacy, if a conjugacy class in SN lies in AN, whether it is still a conjugacy class inside AN or not, that we have to make sure. We will do that using what we have just proved. So look at 1 2 3. So with 1 2 3, certainly we can take 4 5. It's an odd permutation. This commits with 1 2 3. So therefore the conjugacy class of 1 2 3 in SN is exactly same as the conjugacy class of 1 2 3 in AN. Okay. So therefore, yeah, the conjugacy class of that there, and therefore the conjugacy, we will make a list first. Let's make a list. So we will find on the left, we will write down the representatives. So identity, certainly. So and the size, let's just write the size. So the size of the conjugacy class of identity is just 1. Then we have seen 1 2 3. So the conjugacy class of 1 2 3. So all these are representatives in A5. So that has size 20. Okay. Now let's go back to the earlier list. So yeah. And now what happens to that? You see that 1 2 3 4 is same as 1 2 3 4 1 2. So that means 1 2 is we get an odd permutation, in particular the transposition, it comes with 1 2 3 4, and thus the conjugacy class of this is also the conjugacy class of this in SN is same as the conjugacy class of that in AN. So therefore we have, so therefore thus the conjugacy class of this as it the conjugacy class in of this in SN as it lies in AN. So its size, so it has a size 15. So we computed this in the last video. So this is size 15. So yeah, so as I said that out of 7, only 4 conjugacy classes are allowed to lie in AN. So identity is trivial. This is also we have seen, and it's and the conjugacy class of this remains a conjugacy class of this. In the conjugacy class of this in SN remains a conjugacy class of conjugacy class in AN. same for that. But now we will show that the situation is slightly different. Situation is different from that because it's quite easy to see that uh, 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 no no odd permutation indeed no odd permutation indeed commutes with that is very easy to see. So therefore the conjugacy class of this in Sn will be actually will split into two conjugacy classes inside An. So one will be the conjugacy class of the 5 cycle itself, okay, and the size of that will be the half of the original size. So earlier the size was 424, so now it will be 12. And the as I said, the conjugacy class of this in Sn now splits into two conjugacy classes inside An. So the other conjugacy class will be simply 1 2 1 2 3 4 5 and 1 2. So the conjugacy class of this guy, and this is easily seen to be 2 1 3 4 5. So let's just erase the irrelevant ones. So this gives me another conjugacy class inside A5. So thus A5 has 1 2 3 4 5 distinct conjugacy classes. Recall that how we have seen first we when we are dealing with a normal subgroup, we know that if a conjugacy class, so if when we are dealing with a normal subgroup N of a finite group G, of a group G, then we know that either a conjugacy class will lie entirely inside N, and that means so either a conjugacy class will lie entirely inside N, or it will lie totally outside N. That is, the conjugacy class does not intersect with N. That is very easy to see, because if for some x, Gx inverse is in N, from the normality it follows that X is also in N. So therefore, so these are the, so the in S5, these are the representatives of distinct conjugacy classes. So we immediately check that only four conjugacy, only four of them, which are represented by one, this and that, this and that. Only four of them are allowed to be inside A5. But now we have to see that whether the conjugacy class in Sn will remain as a conjugacy class inside An or not, because as we have seen earlier that it may split into two parts. It may split into two parts. Let me again explain, so you should not get confused that, so if N is a normal subgroup of G, any conjugacy class in G lies in N or disjoint from N. This is what we have seen. This is what this is what is clear from the normality. Okay, so the conjugacy class in G, be mindful. So if sigma is in An, then this entire conjugacy class, let me just erase the thing, then this entire conjugacy class, try to understand what is happening. So if sigma lies in An, then this entire conjugacy class will certainly lie inside An. Certainly it lies inside An, it doesn't go outside An. But this is not going to be a conjugacy class inside An. I mean, this may not. Well, again, let me repeat. So certainly this lies entirely inside An, but this may not be a conjugacy class inside An. Okay. So either this will, so it may be a conjugacy class inside An, or it may split into two conjugacy classes inside AN. This is what we have, and therefore we will now check that whether these conjugacy classes in Sn will be conjugacy classes in An as well or not, and that checking will be made in terms of finding a transposition or not permutation, and and yeah, so here it is easy to see that for this and for this and this, that we do have a conjugacy class, we do have a odd permutation which commutes with in these two cases. In either of these cases we do have an odd permutation that commutes with that. But so therefore their conjugacy class in Sn is again going to be a conjugacy class inside An, but the situation differs in case of this. It's easy to see that it doesn't have there is no odd permutation that commutes with this because of its this 5 cycle, because yeah, there is no odd permutation which commutes with that. Okay, and once this is there, so therefore the equivalence class of this in Sn, though it lies inside An, but it will now split into two conjugacy classes in An with equal size. So one of them is the conjugacy class of this itself, conjugacy of this one itself, the other one is the conjugation of that by this. All right, okay, so I think now it is clear, and their sizes are also in the first two cases, the sizes are same as those in Sn, but here the conjugacy class of this inside Sn that has order 24. Now it will be divided into two parts, 12 and 12. All right, I think with that I will stop here.